Hey, how's it going? Mr. Dent here. Today I want to give you an introduction to vectors. And then I also want to talk about adding vectors graphically. Okay, in this screencast, here's the things I want you to learn. First, I want you to know the difference between a vector quantity and a scalar quantity. And then I also want you to be able to add vectors graphically. So let's get started. So a scalar would be a physical quantity that has only magnitude but no direction. Now a vector is a physical quantity that has both a magnitude and a direction. Now just to clear this up, magnitude refers to the size of the quantity. So like if I gave the displacement, so displacement is a vector quantity, I would say 35 meters, so that would be the magnitude part, and then the direction would be east or to the right or up. Now here's a few quantities that we often get confused with one another. They're easy to get mixed up because they have a lot of similarities, but there are the differences because of our definitions of a vector versus a scalar quantity. So distance and displacement, they are similar to each other, but they are different. So distance is basically the length of the path that the object actually travels. Sometimes an object doesn't travel in a straight path. And so in those situations, the distance and displacement would not necessarily be the same. And then a vector is a straight line between the start point and the end point. Now we've had these terms already, so I don't have them as far as the definitions displayed. But they are easy to confuse, so I think it's important that we review those. So speed and velocity, the same thing. They get confused with one another often. And so speed is going to be the total distance covered, and that would be divided by the time that it took to actually cover that distance. Velocity, on the other hand, is going to be the displacement divided by the time. And so displacement and velocity go together. That's why I have them they're arranged on top of each other in this chart, and then distance and speed also go with each other. Anyway, so let's look at an example where we would have differences in these terms or these different quantities. So distance, we'll compare distance and displacement first. So let's say we have a situation, we have a 400-meter track as shown in our picture, or shown in this diagram just below, and it's kind of a rough, I know it's not perfectly, that's not how a track is actually shaped. But anyway, so it's a 400-meter track, so the length, if the distance around this track, or the length, if I ran all the way around this, would be 400 meters. So let's say we had someone and they took one lap, exactly one lap around the track, and so they start here at this spot, and then they also end here. So here's our start point and our end point right at this spot here. And so the distance would be 400 meters. However, the displacement would be 0 meters because we started, our start point and our end point, they're at the same place. There is no straight line between them. So displacement would be 0. And since displacement is a vector quantity, we have a magnitude, so there's the magnitude, but it's 0, so we can't really have a direction in this case. So let's say we did this in 60 seconds. So let's say it took us 60 seconds. Actually, we would be running for this to occur. Actually, we'd be running fairly fast. And so let's say we wanted to find the speed of that. So we would have the 400 meters, and this is all review here from previous chapters. So 400 meters divided by 60 seconds is going to be 6.7 meters per second. And so I'll go ahead and write that in this box. So 6.7 meters per second. So what would the velocity be? Well, since velocity is is referring to the displacement, so velocity, is equal to change in position divided by the total time that it took to do that. Well, in other words, displacement, so displacement was 0 in this case, so velocity has to be 0 also. So here we have situations where they are going to be different from one another. Now we've already seen this in previous chapters, so this is a review. Okay, so here's some other examples of vector quantities, and so I thought it would be useful if you see how that should look when you're asked to give, okay, what was the displacement, what was the velocity, so on and so forth. And so we should always see a magnitude, and we should always see a direction. So here's some various examples. So we have displacement 23 meters south, or 4.8 meters per second for a velocity. And if it was at an angle off of our south and west, using cardinal directions, we would have to give it an actual angle, and that's something that we will learn in the screencast. Acceleration, okay, that's also a vector quantity. We could say up or down, or it just depends on what it was. And then force, which we will not talk about in this chapter, but we will talk about it in previous, or actually in chapters to come up. We would do those in upcoming chapters. We will talk about force, and so we would always need to give a direction for those. It's really easy to kind of get forgetful of that. Okay, so the next thing that we want to cover in the screencast is vector addition, and so a couple terms and some background stuff, to help us do operations with vectors, math operations. So one quick definition, and we'll see this term quite a bit, is the resultant, or sometimes it's called the resultant vector. And so the resultant is a vector representing the sum of two or more vectors. So in this picture I'm showing you here, I have this displacement vector here shown by line A, and then I have line B also, and so there are two displacement vectors, and so if we add them together, this dotted line would be the resultant. And so today we're going to learn how to do that graphically. But just some information before we do that, I think this is important. We know that vectors can be added in any order. So in this diagram, we have basically in part A here, we have this vector going north. This would be going east, north again. Then we went west, and then we went north again. And then the way we do this on graphically, we would draw a line from the first, or the tail of the first vector to the tip of the last vector. And so when we draw these vectors, we're going to have the tail and then the tip, and we would put a arrow at the pointer at the very end on the tip. And so we would arrange these tip to tail, tip to tail. Now it doesn't matter which order you do them. So here in B, we're showing the same set of vectors, but only drawn in a different order. As you can see, they give the result, or the resultant is the same for both of those. Okay, so when we subtract vectors, basically you're adding its opposite, or basically the negative of the vector. So a negative of a vector is going to be the same magnitude but opposite direction. So example, if we want the opposite, or the negative of 30 meters per second west, we could word this as negative 30 meters per second west, or we could also say it's 30 meters per second east. So both putting the negative sign makes it opposite, or when we're using the directions like on a map, we could just say the opposite direction. Okay, so now let's talk about multiplying or dividing vectors by scalar quantities. So when we do that, we're going to end up our result is also going to be a vector. So when we divide or multiply a vector by a scalar quantity, we are going to get a vector quantity. So for example, let's say we're going 10 meters per second north, and we wanted to just double that speed, which basically turns into multiplying it by 2. 2 has no direction, so technically it's not a vector quantity. So you would end up with 20 meters per second north, and it would still be a vector quantity.
Flight 209er, you are cleared for takeoff.
Roger. Huh?
LA departure frequency 123.9er.
Roger. Huh? Request vector. Over. What?
Flight 209er, clear for vector 324.
We have clearance, Clarence. Roger, Roger. What's our vector, Victor?
Howard radio clearance, over.
That's Clarence, over. Over.
Roger.
Huh?
Roger, over.
What? Huh?
Okay, let's go ahead and get going with the adding perpendicular vectors using the graphical method. So here's the steps or the how to do this. So what I would do is pause the video and write these things down. Now the first item on that list is basically, kind of the rules of how you represent vectors on graph paper. And so the length of the arrow, the length of the line of your arrow is going to represent the magnitude of our vector. And then the direction that the arrow is pointing is going to, it just makes sense that that's the direction of the vector. So go ahead and pause the video and write these down, and then we'll go ahead and get started. Okay, so our first problem, so we have Lloyd. He's riding a mini bike in Aspen, Colorado, and so he's going to go 10 blocks north. So that's one displacement, and then he's going to go 7 blocks east. So we have two displacement vectors, and so we want to know his total displacement. And I know it doesn't say what is Lloyd's total displacement, but essentially that's what it's asking. And so the first thing you want to do is establish a scale with your graph paper, and it's just you want to choose something that's going to be convenient and not confusing for you to use. So I think it makes sense in this situation that we're going to make each city block be equal to 1 square on the graph paper. The second thing you want to do in this step is you also want to go ahead and measure the actual length of the squares on your graph paper with a metric ruler. And so I've done this, and so I've measured each one of those as being 6 millimeters as indicated there at the top. And I would write these things there on your graph paper, or write them down somewhere where you have that to use later. And so if you're always using the same graph paper, once you have, that each square is 6 millimeters, you can just continue to use that. Okay, so the next thing we need to do is draw our vectors on the graph paper. So as indicated in the steps, the length of the arrow is going to give us the magnitude, and the direction that it's pointing is going to be the direction. So I've drawn our 10 blocks north, so that was our first vector, and then I've drawn the 7 blocks to the east as shown here in the on the graph paper. So here I got my 10 blocks north, and then I got 7 blocks east. So the next step is going to be drawing our resultant vector. So the resultant is just going to be a line that goes from the tip, actually the tail I should say, the tail of the first vector, and you're going to draw that straight line, draw a straight line. So you could use a ruler here, draw a straight line to the tip of the last. So let me say that again, the tail of the first to the tip of the last. And so this will represent our resultant vector. And so the length of this is basically going to represent the magnitude, and the direction that the arrow is pointing is going to be the direction of our resultant.
I gotta stop. We're going to the bathroom.
Just go, man. Oh. That sure is warm.
And so, so this next part is a little bit confusing. So you may have to pause the video a few times, maybe jot down a few extra little bits of information as I talk about it. So the first thing we want to do is we're going to use a ruler to measure the length of the resultant that we drew on our paper. So I've laid down the ruler, and so I've measured that as 75 millimeters. See right here. So 75 meters, just so 75 millimeters is what I've measured that. So, you know, it's 7.5 centimeters, but it's 75 millimeters. Since I had my squares as being 6 millimeters, that's going to be important later. Okay, so once we have that done, then we can go ahead and do some conversions using conversion factors. So since each square is equal to 6 millimeters and each square also represents one city block, we can convert our measured length drawn on our measured length of our resultant, and we can actually eventually convert that to city blocks. So I just took, I have 75 millimeters, which I measured, and then I'm going to multiply that by my conversion between squares and millimeters. So each square is 6 millimeters, so I have my conversion factor for that, and then I also have the conversion between city blocks and squares. So I'm going to end up with 12.5 city blocks. That's going to be the magnitude of our vector. So this right now at this point we're not done. We have to give a direction also. So magnitude is what we found so far. And so the next part is we need to measure the angle of the resultant using a protractor. Now this becomes confusing sometimes, so a general rule that I think you should always try to follow is we always want to measure our angle off of the east-west line, or in other words the x-axis. And so in this case I have I've added a blue line to show you here that this is what we're measuring from, and then this little curved arrow saying this is the angle. So I'm measuring the angle between this east line and the actual of our resultant vector. I know you might be tempted to measure this angle or maybe this angle, but this is the angle we want to measure. So it's off of our east-west line. Now this is in cases of when we're on a coordinate plane where we aligned our coordinate plane with north, south, east, west type of system. And so we would lay our protractor down and measure that, and make sure you're sure of how the reference points on your protractor. Some of them are different, so please pay attention to that. And you also want to make sure you use the correct numbers. So here, since I'm coming off of this line, and my inside numbers on my protractor are the ones that start at 0, so I would use those. I wouldn't start with these because this starts at 180 and goes down, and that would give us not the right thing. So let's say you made that mistake and did that, and your line is at 125 if you use the outside numbers. Well, does that make sense that this angle would be 125 degrees when we know that a right angle is 90? So it has to make sense. So make sure you're using the correct set of numbers on your protractor. So I measured that as, and I'll go back real quick. So if we look at that, we can see here that we're at 50, and it's like right, and I know my line was kind of fat, so basically it's between the 5 and the 4. So here's 50 right here, and then it's in between the 5 and the 4. So I'm going to call that as 54.5. And so my measured angle was 54.5 degrees. And here's, let's see, I don't have the magnitude. Actually, I do. I went ahead and wrote it here. So I have the magnitude here. And so just to have our reported answer, it's going to be 12.5 blocks, 54.5 degrees north of east. So this, you know, and students ask me a lot, how do I know what to say here? Again, I think you just have to think about what's happening here. This is our east line, you know, and since we referred from that, you know, this line is north of that, so 54.5 degrees north of east, or you could also say 54.5 degrees northeast. So our complete answer in this case is 12.5 blocks, 54.5 degrees north of east. Okay, so before I close here, I wanted to show you, and we won't do this complete thing. I'm going to have you kind of do it on your own. Let's say we have more than 2 vectors. So here I have 4 different vectors. So I have 7 kilometers south, and I have 6 kilometers east, then I went 3 kilometers north, and I went 5 kilometers east. So we follow the same procedure basically. So don't let the fact that just because we have multiple vectors here change your procedure. It's still the same. So we would establish our scale. You know, in this case, since we were in kilometers, I would say each square is worth 1 kilometer. That's easy to do. And then since I'm using the same graph paper, each of those is going to be 6 millimeters. So let's go ahead and draw our resultant. So remember, we do it the exact same way. As I said before, we go from the tail of the first. In these cases, I think it's actually useful if you label the start, put S or put start there, and then label the end as end, or put an E there to say, okay, that's the end, this was the start, I know where to draw my line. So then you would just draw your straight line as I've shown with this sort of greenish colored arrow. And you may even want to label that. I think that's a good idea to do that. So this is my resultant vector, and then I would follow the procedure as stated before. So let's do this. Let's go ahead and pause the video, and then I want you to finish the rest on your own. Okay, so after you've hopefully you actually did pause the video, and here's the actual final, or what would be the answer. So I measured that resultant as 71 millimeters, and then I since each square was 6 millimeters, I converted that using conversion factors, and I made each kilometer worth 1 square. So I'm going to end up with 11.8 kilometers as the magnitude of my displacement, and then I measured with my protractor that as being 20 degrees south of east, because here's my where's my cursor? There it is. This right here is my east line, and since this is my resultant is south of that, so that would be 20 degrees south of east. So my complete answer is 11.8 kilometers, 20 degrees south of east. Remember, you have to have a magnitude, and we have to have a direction. In some cases, we have to have an actual number of degrees for that to be a complete answer.
We're there.
Got a little dippy going too the fast side here.
Okay, so this pretty much concludes this screencast. I hope you got something out of it, and I hope you enjoyed watching the screencast as much as I enjoyed making this screencast. I will see you in class.